one atom of that element, and you're determining where the most stable state of the electrons in the orbitals of that atom. But how often do we have free atoms? Like never. The only elements on the periodic table that really exist as free atoms are noble gases. And so most of the elements in the periodic table combine with other elements in making compounds. And so the question becomes, what happens to these orbitals when compounds are formed? Again, when you're coming up with electron configuration, it's the most stable state of the electrons in an atom of that element, or in the case of ions, if it's a main group element, the electron configuration of a cation or anion is the same as a main group element or noble gas that is an atom. When you get in the middle of the periodic table, determining electron configuration of transition metals is a little different, and you may have a homework problem about that. But essentially, the s orbitals, the electrons get removed from those first before they're removed from d orbitals. There's a slide in the PowerPoint about that. There's no questions on the exam about ions that are formed by transition metals. And so, essentially, when we talked about ions that are isoelectronic with atoms of elements, it's pretty easy. The examples we are looking at were ones of main group elements. If they lose electrons, they simply want to have the same electron configuration as the nearest noble gas. Or if a nonmetal like chlorine or fluorine or bromine gains electrons, again, they want the same electron configuration as the nearest noble gas. But there's a couple of concepts before we start this chapter 9. There's some concepts that I might have alluded to, and I'm not sure how thoroughly I went over them. A couple of them are on the study guide, and a couple of them aren't. So let's put these up here. We want to kind of think about examples of these things. So I just want to make sure this kind of definition stuff, but you have a periodic table, and that's included in this packet I gave you. Does everybody have one? Anybody come here late? Did you get one from? Great. Well, you have electron configurations of the entire periodic table in the packet I gave you. But when you have electron configuration, it doesn't actually show the individual orbitals. And so we want to do some simple ones again using an energy diagram, maybe the first 10 or 11 or 12 elements in the periodic table. And the orbitals in order of energy here and so we're not going to go too far up, and the energy increasing in this direction. And just looking at these definitions, I think everybody kind of knows the Pauli exclusion principle. If an atom has more than one electron in it, no two electrons in an atom can have exactly the same set of 4 quantum numbers. And at least one of the numbers has to be different. And let's think of the simplest element, hydrogen, first. Using the energy diagram, the lowest energy orbital that's available, or the 1s orbital, hydrogen has one electron, and so it's in the 1s orbital. We said its electron configuration is 1s1. That means there's one electron in the 1s orbital. And these orbitals are derived using the rules of quantum numbers. We said that n has to be an integer 1, 2, 3, or 4, 5. And so in this first energy level, n is equal to 1. We said L can be 0, 1, 2, 3, up to n minus 1, but if n is equal to 1, 1 minus 1 is 0. So L has to be 0 when n is equal to 1. And m sub L ranges from minus L to plus L as integers, but if L is 0, m sub L has to also be 0. And then there's two possible spin quantum numbers, and we'll just, there's plus 1/2 and minus 1/2. And so we'll just say, and we're not going to belabor the point, but these are the 4 quantum numbers for this first electron that hydrogen has. Okay? Then we say it's in a 1s orbital. Now everyone again knows the rules of the Pauli exclusion principle, that no two electrons in an atom can have exactly the same set of 4 quantum numbers. So when we go to helium, if it's an atom, it has 2 electrons, and this orbital can have up to 2 electrons in it, but they have to have opposite spin. So for helium, its electron configuration is 1s2, and one of the electrons has these 4 quantum numbers, and the second one, n's the same, L's the same, m sub L's the same, but it's got to have one that's different, and so it's the spin quantum number is minus 1/2. Okay? And that's the second electron that I just added to this orbital. So we satisfied the Pauli exclusion principle. Also, Aufbau principle. Did we talk about that at all? Aufbau is from the German, building up. That's what we're doing right now. When you assign electrons to orbitals in atoms, and that's what we're doing right now, you simply start at the lowest energy orbitals and you work your way up. That's all we're doing. Okay? And so this orbital's filled now, so when we go to the next atom on the periodic table, lithium atom has 3 electrons. Well, 2 of them are in the 1s orbital, and it's filled now. So the third electron has to be in this 2s orbital, doesn't it? Okay? So its electron configuration is 1s2, 2s1. There's 2 electrons in the 1s orbital, and 1 electron in the 2s orbital. Does it have a unique set of quantum numbers? Of course. The third one, and I'm going to stop doing this, but this electron here, now n is equal to 2, and one of the possible values for L is 0. In fact, for all s orbitals, L is equal to 0. And so m sub L has to be 0. And the spin quantum number we'll just say is 1/2. And so it's got a unique set. And we're going to stop, but you get the idea. As I keep filling these, each additional electron I add is going to have at least one quantum number that's different. And so we can stop worrying about this. But you just saw the Aufbau principle in action, because this orbital's full. With the Aufbau principle, you fill the orbitals from the lowest energy and work your way up. That's all it means. Okay? Now, it's going to be a while before we get to the p orbitals on your periodic table. Okay, next in the periodic table, of course, is beryllium. It'll have 4 electrons. I'm kind of running out of room here. Beryllium, well, we could put another electron here with the opposite spin, and again, it'd have 3 of the same quantum numbers as this one, and then at least one quantum number is different, the spin quantum number, and so it has a unique set. And I'm going to discontinue worrying about all this. We've talked about this before, but these orbitals are all a manifestation of these rules for quantum numbers. I mean, when we finally get L equal to 1, then you have p orbitals, for example. Well, for beryllium, it's simply going to be 1s2, 2s2. Okay? Well, now we go to atoms that we need to start filling these p orbitals. And this is where you see Hund's rule. And did we talk about Hund's rule at all?
A little bit.
A little bit. All Hund's rule says is that if you have orbitals that have the same energy, well, you have to assign 1 electron to each first before you pair them. Don't forget that electrons have negative charges, and so they repel each other. So you want to put 1 electron in each of these 3 p orbitals first before you pair them. Okay? And you can't see that yet. Next element, of course, is boron. And boron having 5 electrons, we'll just put 1 electron in the 2px here. But when you write the electron configuration, it doesn't distinguish between x, y, and z for the p orbitals. You just know you can have a total of 6. But electron configuration is 1s2, 2s2, and now we have 2p1, don't we? Well, we'll see this effect, the Hund's rule effect, with the next element on the periodic table, which is carbon. Because carbon has 6 electrons. We put 2 here of opposite spin, 2 here of opposite spin. And you might be inclined to want to put it here. But according to Hund's rule, you can't do that. You have to spread the electrons out first. And they have the same spin as well. And so Hund's rule simply states that when you have orbitals of the same energy, you have to have at least 1 electron in each of these orbitals before you can start putting the second electron. That's all it really is, okay? It's Hund's rule, not Hunt's, so don't blame me. We'll see this with the next, well, this is carbon's electron configuration, 1s2, 2s2, 2p2. After carbon, of course, you got nitrogen. Well, with nitrogen, it's going to have 7 electrons. 1, 2, 3, 4, 5, 6. Again, Hund's rule, we got to spread it out. Does everyone see if we have this type of representation? This is how you show the electron configuration for nitrogen. Hund's rule, you spread the electrons out first before you pair them. You don't see Hund's rule when you write the electron configuration this way. Because we just, for the p electrons, we just go all the way up to 6. And you don't see the individual orbitals. Okay? Everybody see Hund's rule here? And just to finish up, oxygen, now we have 8 electrons. 1, 2, 3, 4, 5, 6, 7. Now we can start to pair them. We don't pair them in a p orbital until each orbital has 1. This is, again, just what Hund's rule is referring to.
So Hund's rule only refers to the p orbital?
Well, it also applies to d orbitals, but we're not going up that high.
Just for p.
Whenever you have orbitals that have the same energy, you put one electron in each of them first before you pair them, except that I don't want to get too much into the d orbitals because they play tricks. There's glitches and exceptions. But for sure, the p orbitals. Because you'll also encounter p orbitals up here in the third energy level, and every subsequent one, yes. For p orbitals, you have one electron in each first before you pair them. As a manifestation of Hans' rule. What do we got? Fluorine next, and then go up to neon, I guess. One thing about the noble gases, as we the new p orbitals get filled. So, for example, if chlorine's 3s2, 3p5, well, you know, argon's 3s2, 3p6. The p orbitals get filled by the time you get to the noble gas, and so you just add one more electron to the p orbitals of the halogens to get the noble gas. Does that, everybody see that?
Mm-hmm. You can have one of those.
Oh, here you go. And this, you can use this, again, you can use this on the test. Okay? All right, we only have a few more here. Run out of room here. Fluorine. Fluorine's going to have 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so fluorine, of course, 1s2, 2s2, 2p5, and then we'll get to the noble gas neon, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's considered a filled level, isn't it? Just like this was for helium. And this is 1s2, 2s2, 2p6, okay? The Heisenberg uncertainty principle, I don't think, and I think part of the reason is there wasn't a slide that discussed it. And it's really kind of an important idea, even though you don't use it for determining electron configurations or anything. But in studying atomic structure and some of these concepts that we've been talking about, using quantum mechanics. It was actually Heisenberg that showed with a calculation, and this is on paper with a calculation. Heisenberg showed that you cannot simultaneously know the position and velocity of an electron. And that might sound like we haven't invented good enough equipment yet, but that's not the point. Heisenberg showed mathematically that it's impossible to ever know the location and velocity simultaneously of electrons. And it seemed, this bothered some scientists because it's as if nature created electrons probabilistically. In other words, you have to think about it macroscopically. When you're following the trajectory of something like a baseball, a batter hits the ball and it goes through space, and you might have a camera and you're taking pictures of it. Well, what are you actually measuring when you when you take pictures of this baseball that's flying through the air and studying its motion? You're actually getting photons of light that have reflected off the baseball and come to the camera. And photons aren't going to, when that strike the baseball, are not going to affect its trajectory much, if at all. But it's entirely different with an electron. What kind of camera are you going to use to know exactly where an electron is and its velocity at the same time? You would actually be interfering with its velocity if you tried to strike it with a photon. It's almost like a philosophy of science kind of concept, except that it's not just philosophically we can't simultaneously know. It was actually derived with some of these equations we've been working with, that it's simply mathematically impossible to know. And so it kind of suggests that quanta and the smallest particles of matter and energy were intrinsically probabilistic. Einstein hated this principle. He hated it because it seemed to suggest that some atomic phenomena was intrinsically probabilistic. And his famous quote was, God was not playing dice when he created nature. But chemists and physicists still work with it and understand it and use it. And so even when we're talking about orbitals, these are probability densities, where probability electron is going to spend 99% of its time using wave equations. We already talked about the Broglie relationship and wavelength. And this, so really you know this one. It's even on the formula sheet. But any particle that has mass and velocity has an intrinsic wavelength, and you can calculate it, and that equation's on your sheet. But it's only important for particles that are small, like electrons. Okay. I mean, you could calculate your own de Broglie wavelength, but it would be so ridiculously small that it wouldn't be measurable. Okay. So the de Broglie relation wavelength, since visible light had photons and had both wave and particle properties, well, the smallest particles of matter have both particle and wave properties, and you can calculate the de Broglie wavelength, and we have talked about that. But those are just some things, I don't know if I went over them well enough. Let's go ahead and look a little bit at the next chapter, and don't fall too far behind here. And the lab today, we'll be kind of finishing up the experiment, the second half of the experiment we did last week. Okay, so in the previous chapters, we learned about atomic orbitals that electrons occupied in atoms of the various elements. And in this chapter 9, we're going to look at how atoms of different elements form different types of bonds. Earlier in the course, we mentioned really two families of compounds. When you have a metal and a non-metal, metals tend to lose electrons and form positively charged cations, and non-metals tend to gain electrons and form negatively charged anions. And there was a force between these opposite charged ions that we called an ionic bond. And then when you have two nonmetals and you bring the atoms together, they actually have a type of bond that involves electron sharing that we call covalent bonds. And so the question becomes, how do these atomic orbitals generate covalent bonds? Now, for looking at ionic compounds, this is fairly intuitive for the main group elements, because now you have a periodic table that, on your periodic table, for the main group elements, you know exactly how many valence electrons they have. And you can kind of see they all have a new principal quantum number n as we go from one period to the next, or row to the next. But the valence electrons have these general electron configurations. These are the outermost electrons for these groups. And you can kind of see for group 1A, the alkali metals, and group 2A, the alkaline earths, that if the alkali metals lose this s electron, well, now you're going to have a filled shell below it. And this is the driving force for sodium atom forming a sodium cation, potassium atom losing an electron to form a potassium cation with +1 charge. In the alkaline earth, like calcium and magnesium, the valence electrons are in a s orbital, and if those atoms lose those 2 electrons, and now you're going to end up with a cation with a +2 charge, and this is the way we find calcium and magnesium in nature, with a +2 charge. If they lose those outer s electrons from that s orbital, then they've got a filled shell below it. They've got an electron, when they lose these metals here, group 1A and 2A, when they lose those valence electrons, they end up with an electron configuration of a noble gas, and you're gonna have a filled shell. It makes them very stable as ions. And here at 3A, of course, aluminum, it loses 3 electrons, 2 from an s orbital and 1 from a p orbital, and it also will have, it'll have a +3 charge, and it'll have the same electron configuration as the noble gas neon. Well, when we get to the halogens, of course, what happens is the non-metal halogens, if they gain 1 electron, then there will be 6 in this p orbital. This valence shell has 7 electrons. If they gain 1 more electron, then they'll have the same electron configuration as the noble gas right next door by gaining an electron. And that's what happens. So group 7A, chlorine, bromine, iodine, they gain 1 more electron and they form an ion with a -1 charge. Oxygen, sulfur, gains 2 electrons and have a 2- charge to fill the p orbitals. Nitrogen, phosphorus gain 3 electrons and have a 3- charge. So you can kind of understand the charges of the ions that are formed based on the electron configuration of the valence electrons. Here's what we call Lewis dot structures, and Lewis dot structures just show, for the main group element, dots that represent the valence electrons. Of course, all the alkali metals have 1 valence electron. Chemists use Lewis dot structures for convenience in trying to rationalize why certain molecules form and why certain ions form. We generally don't use Lewis dot structures with transition metals. We don't use the concept of valence electrons for the transition metals. They have their own set of rules, and some of them form more than 1 ion. And we've talked about that. But we can use these dot structures to represent valence electrons. And of course, for the noble gases except helium, they all have 8, and they have a filled shell as far as their valence electrons are concerned. Well, here we can kind of see with Lewis dot structures, if we have the element of the alkali metal lithium, and we bring it together with an atom of the halogen fluorine, well, fluorine will take this one valence electron away from lithium. Now the lithium has the same electron configuration as the noble gas helium, but it has a +1 charge. For fluorine, when it gains an electron, it has the same electron configuration as the noble gas neon, but has a - charge. And we say we formed an ionic bond. Ionic bonds are the strongest of the types of interactions. Essentially, a lithium atom is losing an electron, a fluorine atom is gaining it, and we're making the compound, the ionic compound, lithium fluoride. Now here it mentions a lattice energy, and this is the energy required to completely separate 1 mole of a solid ionic compound into gaseous ions. And this this is kind of a classical equation from electricity and magnetism, but the potential energy here is equal to a constant times the magnitude of the charges on the cation and anion as integers, and then r is the distance between the ions. And of course, lattice energy increases if Q increases. So if Q is, let's say, +2 for calcium as opposed to +1 for sodium. Now, they've come up with a way, this gets back to what we talked about in thermal chemistry and Hess's law. There's certain things, certain physical phenomena involving compounds or elements that we can determine in the lab. And because enthalpy is a state function, in order to be able to determine the lattice energy of a compound, if we can determine some of these other changes in enthalpies, then we mathematically can calculate the lattice energy. And the lattice energy, of course, energy required to completely separate 1 mole of the solid ionic compound into gaseous ions. So on this Born-Haber cycle, here are gaseous ions for lithium cation and fluoride anion, and they're separate from each other. And here is the ionic compound, lithium fluoride, that has the ionic bond. So this transition here as essentially involves the lattice energy, and if we can figure out these other parameters in this overall process, we can calculate what H5 here is, which is essentially the lattice energy. You have to look at this one step at a time. They can experimentally determine this first step. Here you've got lithium solid, and they can measure how the heat required to make gaseous lithium atoms out of lithium solid, and this is delta H1 in this process. Here, this involves bond energy. Here you've got a fluorine gas as a diatomic molecule. We can experimentally determine the bond energy that it takes to break F2 into F atoms, and that's here. What's going on here is a series of processes that will ultimately take us where we want to be. Also, this and change of enthalpy overall, we can determine straightforward in a chemical reaction the enthalpy overall of the heat involved when you react lithium solid with fluorine gas to make lithium fluoride. So we can determine that step. The point of this diagram is we can determine all these steps and except this one, and then mathematically we can determine what this is. This is a process that physical chemists can use to determine the lattice energy for an ionic compound. But they either have to do all these other processes and measure them, or get them from the literature. And then when you know everything else except delta H5, then you can determine delta H5, can't you? Here you see some lattice energy. So notice that magnesium and calcium, don't forget in that original equation, they have a +2 charge. Their value of Q is going to be +2, and notice how high their lattice energy is, and this translates into extremely high melting points for these ionic compounds. Let's see, where are we at now? Now, covalent bond is a little different, ionic bond, although for nonmetals that are main group elements, covalent bonds, we can still use Lewis dot structures to try to justify the formation of molecules. Here's an example. Fluorine is one of the elements on the periodic table that's a gas, and it's also diatomic molecular element. That means it exists in clusters of two. So even when we have the pure element fluorine, it doesn't exist as individual atoms, but it actually exists in clusters of two. And these Lewis dot structures, they're very traditional. They've been around for many years. They don't tell you anything at all about the shapes of orbitals or anything like that. It's just the notion that we can kind of justify why certain molecules form based on their wanting to have an octet in their valence shell. So if we look at two fluorine atoms, and we draw the Lewis dot structures, each of these fluorines has 7 valence electrons, but if they form a covalent bond and share 2 of them, so we'll use these 2 are being shared here, and they still have their others. If you are sitting on this fluorine, it now has an octet around it. If you're sitting on this fluorine, it has an octet around it. And so the early justification for the forming of molecules using Lewis dot structures was that it enabled the molecule of the nonmetals to have 8 electrons in their valence shell, similar to a noble gas. Well, whenever you have 2 electrons being shared, you can write it as a single covalent bond. And so another way of writing the Lewis dot structure for fluorine gas is like this. This covalent bond is 2 electrons being shared by both. Okay? Here it shows you example, well, with water, oxygen has 6 valence electrons, and of course hydrogen has 1. If oxygen forms 2 covalent bonds with these 2 hydrogen atoms, now the oxygen has an octet around it. The hydrogen, of course, doesn't. The hydrogen really has 2 electrons around it. It's similar to helium. But, so it's not, the hydrogen is not obeying the octet rule, so to speak, but the oxygen is. And so we justify water, oxygen forming 2 covalent bonds to end up with an octet in the valence shell. We find other types of bonding. And here's carbon dioxide. When you bring 2 oxygens and a carbon together, you can have an octet around all 3 atoms if the carbon forms 2 double bonds. When you're looking at double bonds, that's 4 electrons being shared instead of 2. And so this is another type of covalent bond. We can also have triple bonds, and this is the way that we find nitrogen in the air as an element. It has a covalence of 3. It wants to form 3 covalent bonds. So if you bring 2 nitrogen atoms together, it forms a triple bond. A triple bond is a total of 6 electrons being shared. 3 times 2 is 6, okay? When you have multiple bonds involving the same element, and carbon can form single bonds, double bonds, or triple bonds, generally speaking, the multiple bonds have shorter bond lengths than single bonds. And so just the general rule, the bond length of a single bond is greater than a double bond, which is greater than a triple bond. And we have ways of experimentally determining bond lengths. Here it shows you a chart of some typical bond lengths involving carbon and other elements, or carbon to carbon with a single bond, carbon double bond. And these are in picometers. Milli, micro, nano, pico. A picometer is 10 to the minus 12 meters. It's extremely small. When you have a polar covalent bond, and we'll take a break here in a minute, you have two nonmetals that have different electronegativities, different electron affinities. And for example, if a hydrogen forms a bond with fluorine, fluorine is much more electronegative than hydrogen. And so the electrons that are in the covalent bond actually spend more time around fluorine than around hydrogen. And this is an example of a polar covalent bond. It's not a full charge, but the hydrogen is thought of as being partially positive, and the fluorine is thought of as being partially negative. These are small Greek deltas here. So this is an example of a polar covalent bond. Okay? All right, well, and then everybody has one of these packets for the exam, right? If you look in the packet, obviously there's equations on the front. I tried to point out, if you're calculating the energy of a photon and you know its wavelength, the wavelength has to be in meters if you're going to use Planck's constant in joules second. I wrote that on the formula sheet. Also, for the de Broglie wavelength, if you know the mass and velocity of a particle, well, the mass, you have to have it in kilograms if you're using the de Broglie wavelength equation, and the velocity must be in meters per second. And this is to be consistent with the units involved in Planck's constant, which is also on the sheet. Okay? Any question about that? You got electron configuration for most of the elements, I'm sorry. On the periodic table, you got some more on the sheet there. I think you want to try to understand how we did the simple ones today. Here, there's a sheet that shows you the different allowed values of quantum number for n equal 1, 2, and 3. When n equal 1, of course, all you can have is an s orbital. When n is equal to 2, you can have s orbital and 3 p orbitals. When n is equal to 3, you can have an s orbital, p orbitals, and 5 d orbitals. And so the number of orbitals increases. Got handouts here on just the nature of the 4 quantum numbers, the rules for the quantum numbers. And you have to keep in mind when it says for a given value of n, L equals, for a given value of L, M sub L equals. So you have to know what the previous quantum number is to discern what the possible values are for the next one, and so on. And then you got a periodic table. Okay. All right, let's look at a few more slides, and then we'll hit the lab. The lab, of course, will be short. Electronegativity is the ability of an atom to attract electrons in a covalent bond. Electron affinity is actually measurable, and electronegativity is relative. And so they use one to help determine the other. But if you look at a periodic table, that has electronegativities on it. And again, the electronegativity is a relative phenomenon. You don't see any units here. But you see for fluorine, electronegativity of 4, and it's the largest value of electronegativity on the periodic table. And then you look at, let's say some alkali metals, like cesium is 0.7, which is quite low compared to fluorine. And you can actually predict, if you have a table of electronegativities, you can kind of predict whether two elements are going to form an ionic compound, or if they're going to form a polar covalent bond, or if they're going to form a non-polar covalent bond, simply by subtracting the electronegativities. And on the periodic table, we already know, we talked about this before, metals generally react with nonmetals to form ionic compounds. So we expect their difference in electronegativity to be substantial. And here you've got, if you took something like lithium, which has an electronegativity of 1, and fluorine, an electronegativity of 4, fluorine is 4 times as electronegative as lithium is. When you subtract that difference of 4 minus 1 is 3, should predict that they're going to form an ionic bond, and therefore an ionic compound. On the other hand, if you have an oxygen bonded to a fluorine, their difference in electronegativity is only 0.5. And so you're going to get a covalent bond. And they're sharing electrons. And here it kind of shows you the variation of electronegativity with atomic number, and the halogens have the most affinity for electrons, the alkali metals the least. And here, very simple, and maybe for the 5th exam, I might even put this slide on the test, but if the difference of electronegativity is 0, it's a perfect covalent bond. And obviously, if, let's say, a nitrogen is bonded to a nitrogen, they both have the same electronegativity, their difference is 0, so that'd be perfect covalent bond. Or any elements that happen to have the same electronegativity. And I don't know if there's any that are exact. Yeah, there is arsenic and palladium here. Boron and arsenic. So if it's essentially, let's see if there's an, here's iron 2.8. Here, sulfur has an electronegativity of 2.5, and so does iodine. So if they form a bond, it's going to be, the difference is 0. It's going to be a perfect covalent bond. Now, if the difference in electronegativity is between 0 and 2, then it's a polar covalent. Something like maybe carbon bonded to oxygen, 3.5 minus 2.5 is 1, and it's going to be up in this range. It's a polar covalent. And then if it's greater than equal to 2, well, you got an ionic bond. One element is literally taking the electron completely away from the other. Okay? Now, here it has some discussions on writing Lewis structures. I'll just draw 1 or 2 examples on the board, and then we'll head to the lab. And I'll pick some simple examples. This is where we'll pick up in a week. I think the exam will probably take the entire class period on Tuesday. So. Well, let's look at some simple examples of drawing Lewis dot structures of molecules. We already looked at water. Maybe I could use a different color. This has any ink in it. You got oxygen with 6 valence electrons. And let's say you bring a hydrogen, and hydrogen has 1, and you bring another hydrogen, and it has 1. And again, you can see when oxygen formed 2 covalent bonds, now it has an octet around it. The hydrogen only has 2 around it, but it's resembling helium, so it's not following the octet rule. But hydrogen tends to form 1 covalent bond. And so, another way we could write it is like this. As a simple Lewis dot structure. If we had something like carbon tetrachloride, well, let's make it methylene chloride. Carbon has 4 valence electrons, and let's suppose you brought 1 hydrogen, and then chlorine has 7. 1, 2, 3, 4, 5, 6, 7. You bring another chlorine. 1, 2, 3, 4, 5, 6, 7. You bring another chlorine. 1, 2, 3, 4, 5, 6, 7. And this is the compound trichloromethane or methylene chloride. And if we actually showed the bonds, we could draw it like this. But don't forget, chlorine has, if you're doing a Lewis dot structure, you gotta also show the non-bonded pairs. So when carbon forms 4 covalent bonds, now it has an octet. Okay? Those are just a couple of simple examples. We'll do some more in a week. And we'll finish up here. What we'll talk about a week from tonight is the concept of formal charge. And this formal charge, a lot of the concept of formal charge has to do with, especially with nonmetals that are in molecules that have an atypical number of bonds. Like nitrogen usually forms 3 covalent bonds, but what about if it has 4? Or if you have oxygen usually forms 2 bonds, what if it has 3, and so on. It's as if one of the atoms within the molecule has a charge on it when it has a different number of covalent bonds than what is typical. And we'll look at a number of examples of that next time too. Let's see who's in town here.